Hi, this video we're going to talking about two force member. Two force member, here's a definition, is a structure body that has forces, only forces, acting on it on only two locations. That's very important. Only two locations. In order to have a two force member in static equilibrium, then the net force at each location, they must be equal, opposite, and collinear. So now let's look at some examples on that. A very simple example, I have just a bar that is a straight line, and there are two force on it. One apply at location A, one apply at location B, because only two locations, right? One is going to be drag A to the left, one is going to be drag B to the right. And this F1 is equal to 10 Newton, and this F2 have to be equal to 10 Newton. They have to equal, both equal to 10, and the opposite, one going to the left, one going to the right, and the collinear. Are they collinear? They are, right? We know in this situation, this AB is at equilibrium, which means it's not going to rotate or translate. All right, that's our example 1. Let's look at example 2. If I have a structure member that is L shape, okay, then one force is applied at A, another force is at B, okay? Then what's this force going to have to be? First, immediately, sometimes based on our common sense, we say, okay, if FA is going this way, 10 Newton, F1 here, and F2 is going downward, they said this is going to be at equilibrium. Do you agree? At equilibrium is going to be, it's what we mean is the force at x equal to 0, which is right for this situation because there's no forces at x direction. Force at y equal to 0, that's correct because this is going upward, so it's 10 positive. This one is going downward, minus 10. That's indeed equal to 0. But however, is this moment equal to 0? Moment is not. Why? Thinking about it, this is going to rotate crazy, right? It's going to rotate this, you know. It's going to be, it's not at equilibrium because moment is not equal to 0. We can go ahead scientifically prove it. We can do moment about any point. If we do moment about A, okay. If we do moment about A, we're going to consider all the moment together. We're going to consider moment of force 1 rotating about A. Also this force 2 rotating about A. Well, F1 is right here, and this force goes through point A, so that's 0. And how about F2 rotating about A? We're going to draw our moment of arm. It's going to be from A to this force. And if that's given, if this is, let's say, 5 meter, and this is 2 meter, from here to here, here to here is 5 meter, then we're going to use 10 Newton force times moment of arm, 5 meter, and that rotation is what rotation? Clockwise, so it's negative. So this answer is negative 50. It's not equal to 0. Okay, so when you have L shape here, if you go up and down force, yeah, it's not at equilibrium, right? Then how about look at scenario number 3. We still have this L shape. We're trying to make equilibrium. You said the top Up and down doesn't work. How about this way? If I have a force that's applied at A and it's pulling to the left, that's my FA. And that's 10 Newton. And I have force that's going pointing at the B, FB, 10 Newton. It's equal and opposite. Would this be at equilibrium? Force is at the X direction. At FA, that's positive 10 since it's going to the positive X direction. And FB is going to negative X direction, minus 10. That equal to 0. That's okay, that's checked. Summation forces at Y. There are no forces at Y, so that's equal to 0. That's checked. However, does this rotate? Again, you can choose any arbitrary moment. Here, if we continue to make A, okay, then this force rotating about A, FA rotating about A, going through that point, that's 0. Then we just need to figure out the FB rotating about point A, right? FB is 10 Newton, and the moment of arm rotating about A is going to be this distance. And that distance, we said it's 2 meters. And we're just going to think about the direction. FB rotating about A, it's counterclockwise, so it's positive. That's give us 20 Newton meter. That does not equal to 0 either. So let's look at example 2 and 3. We're really trying to make this L shape at equilibrium. We satisfy translation every single time, but rotation does work. And you notice each pair, they are equal, they're both equal to 10, and they are both opposite direction, up and down, left and right. However, remember, have to be collinear. In order to make it collinear, what would be the way to make it happen? So now let's go ahead and correct that. We have this L shape. One is pointed at A, one is at point B. Not only equal but opposite, have to be collinear. So how about we just connect the line between A and B? Then we got our answer. If this is pulling, we can do compression as well. If it's pulling, then we have it. This FA, we say it's 10 Newton. FB here is 10 Newton. Then we say this is a true force member, and this is going to be at equilibrium. Let's prove it. Force is at X, and force is at Y. Force, and here you don't even need to decompose because you can just say forces. You can just do. You can just go ahead and change force, sum of the forces equal to 0, which you do. Yeah, you can also decompose if you like. But here, now let's look at moment. Again, we do moment at A. We'll have moment of FA rotating about A. We'll also have to do moment about B rotating about A. What do we notice? FA rotating about A, it's 0. And FB rotating about B, it's 0 because they all go through the same point A. The A is on the forces, so that's equal to 0. Then we have satisfied this two force member. So from this example, we know if a member have only two forces on it, and those two forces have to equal opposite and collinear. Okay. So let's look at this example. I have example 5. I have this structure. Okay, weird shape. I can draw whatever we want, right? And this is point A, this point B. In order to make this odd shape to be at equilibrium, this is of course two force member. Why? Because there are only two forces, and these two forces at only two locations. So that's going to be two force member. Then two force member have to abide by opposite, equal, and collinear. So I connect A and B, and I say this, they can be compression. That's going to be my true force member direction right away. Okay. Now let's look at true force member embedded in the example frames. Later on, you're going to learn frames in statics. For example, here you have many members, right? You have AD member, that's first member. Then you have CEF member. You have BE member. That's 3 members already. They are nailed together. Basically, it's a pinned support. Can you look at these 3 members? Identify which member, or if there's any member that is true force member. Okay, now let's look at A, B, C, D member. Is there only forces? Forces have to be what? At only 2 locations. There's going to be force at A because it's a pinned support. That's going to be reaction support at A. So that's 1. And there's going to be force at D because it's tension right here. Then there's a force at C because they're pinned together. There's a pinned support. There is going to be reaction at B. So this has 4 forces. That's not going to be true force member. So A, B, C, D is out. Now let's look at CEF. There's a force at F because the weight is pulling it down, and there's a support at C, so it's pinned support. There's a support at E, that's a pinned support. The 3 locations. Again, that's out. That's not CEF, it's not a true force member. Now let's look at the last one. How about our BE? There's a force at B because that's pinned at B. There's a force at E. There are only 2 locations because in between B and E there are no other forces. So BE for this situation is our true force member. If you identify a true force member, you immediately know. If I were just looking at FBD free body diagram of B only, I know the force at B and the force at E have to be equal and opposite and collinear. So I know it's going to be connect B to E. All right, hopefully this helped. This helped because true force member is actually going to be quite helpful when you're solving the problem. All right, see you next time. Bye.